Hello everyone, so today I will be going over question 5 of the practice final. So for 5a, the reaction is called oxidation of benzene. You just have to know that it's going to go on the least steric alkyl group, and it's just going to add a carboxylic acid as I've shown here, and that is the only change in the molecule. For question 5b, the reason this reaction will not proceed to the molecule we want is because the second part of the reaction, or the zinc and HCl, is called Clemmensen, and although it does get rid of the ketone group, it would also make the NO2 group into NH2, so it would do both, and that is not what we want. So moving on to the second part of question 5, box 5C, what we should notice straight away is that the first reaction, nitration, creates a metadirecting group, so that way we can use a Friedel-Crafts alkylation, and that's just like chlorine with the alkyl group we want attached to it, and aluminum, and yeah. And then that will just especially since this molecule is symmetric, both the meta groups are the same thing, so this would get the product we want. Moving on to the next one, I actually pulled out the lecture notes for this, and I noticed that the exact chain reaction was used as an example, so that's great. I can't do that during the exam though. But the reason that there's two products is because the intermediate created, the benzyne, the triple carbon bond, it's equivalent in both directions. There's not one that's, more chemically reactive, so that's why there would be two products created in basically equal form. Okay, moving on to part C of the question. This one is pretty self-explanatory as well. So once you draw out the molecule that was given, the first initial step should be just counting the hydrogens. So for E, there's 3 hydrogens, and there is only 1 carbon with 3 hydrogens on it. So obviously this one would be corresponding to E, as I circled here. The next one is 2 hydrogens. There's only 1 carbon with 2 hydrogens on it, so it has to be D is this one. Then it gets a little bit more tricky, but initially we know that the aldehyde hydrogen would have to be the most downfield one, and this is confirmed by the H-NMR chemical shift table. So we know that this has to be A. And then we have to use coupling to figure out B and C. So for B, it's a doublet of triplets, and for C, it's a doublet of doublets. So for this hydrogen, there is a triplet and a doublet, so it has to be the doublet of triplets. And then for the other one, there's a doublet and there's another doublet, so that one has to be C. Initially, when I did this, and on my answer sheet, I made this one, I made this one B, because I was like, oh, it's close to the oxygen, it's more downfield, but the coupling is the stronger indicator. Okay, moving on to the last part. I put ABF, and my reasoning for this is that for C, there's no multiplicity or integration for carbon NMR, and for E, that's also just for H-NMR. For A, both TMC is used. For B, just like how in question A, we did symmetry, that means unequivalent carbons have different shifts, so B is correct for both of them. And for F, exactly what we did for both of them. The symmetry is really important. So yeah, ABF. And that's the answers for question 2, I hope.